Hi guys, in this video let us learn what are binomial trees and binomial heaps. So what all things we are going to cover in this video. First of all, we will understand that what is a binomial tree, okay? Then we will learn different properties of binomial trees and I'll also prove all those properties. And then after we have completely understood what is a binomial tree, we will learn what is a binomial heap in the next video. Then what is the structure of a node in a binomial heap? For each and every node, the structure is different in a binomial heap than a normal binary heap or a leftist heap, right? So I'll also explain the structure of how a node in a binomial heap looks like. And then finally, I'll end the next video by talking about the advantage of binomial heap, that how binomial heap is more efficient than binary heap and sometimes even more efficient than leftist heap that we saw in our previous videos, right? So this I'll cover in the next video. Okay. In this video, we are going to see the first two things, that what is a binomial tree and properties of binomial tree with proof. After we have done that, binomial heap is nothing but just a collection of binomial trees in a particular order. So learning binomial heap will be very easy after we have learned these two things in this video. So first of all, let us see what is a binomial tree. So binomial tree is actually an ordered tree, okay? It is not a binary tree, first of all. It is an ordered tree. What do I mean by ordered tree is that if this is a binomial tree B, it will have an order K, right? So this is so we can represent a binomial tree in this way. So this is a binomial tree with order K. So this is my B0 with a single node. These are a few things that you should know before I draw B1, B2, B3 and B4, okay? Bk has K children at root. So if you look at B0, it should have 0 children at its root. Are there 0 children of root? Yes. So now when we draw a B1, in case of B1, there will be 1 children at the root, okay? But how will the B1 look like? We know it will have 1 child. So we understand that B1 over here should have 1 child at the root. So this root has 1 child. So this we can call as B1, okay? And if you want to see that this Bk, or actually B1, is also following this second rule. So if you look over here, Bk can be formed using 2 Bk minus 1 trees. So is this B1 formed using 2 B0? Yes. You can consider this as a B0 and this also as a B0. So it is formed using 2. So this B1 is formed using 2 B0. So this thing is also true. So these both things are true in this. Now the root of 1 Bk minus 1 will be the leftmost child of the other Bk minus 1. So to understand this rule, let us also draw B2 using the above two things, okay? So if you want to draw B2, we know that B2 should have 2 children at the root. That means the root of B2 binomial tree should have 2 children, correct? So we understand that B2, this B2 what we are going to draw, can be formed using 2 B1, okay? So if we take 2 B1s, this B2 can be drawn, or we can draw the structure of B2. But how will we exactly combine these B2s? So to know how we will combine both of these B1s to make this B2, let us look at the third rule. So this says that the root of 1 Bk minus 1, here this is my K and this is my K minus 1. So the root of 1 B1 will be the leftmost child of the other B1. So the root, this is the root of 1 B1, this is my B1, this entire thing is my B1, this is also another B1, right? So the root of this B1 will be the leftmost child, of the other B1. This is my other B1. So that means that this B1 should be the leftmost child of this B1, okay? So this is my B2, or this is my binomial tree with order 2. So by order 2, I mean that the root of this binomial tree should have 2 children. Does it have 2 children? Yes. One leftmost child is this other B1, and yes, it has 1 and 2 children. Okay, so this is my B2. So now let us draw B3. So according to this, according to the first rule, B3 will have 3 children at root, right? So the root of B3 binomial tree will have 3 children. Okay, fine. And B3 can be formed using two B2 trees. Now my K is 3 and K minus 1 will be 2. So according to this B3 will have 3 children at root, and B3 can be formed using two B2 trees. So this is how a B2 tree looks like. So these are my two B2s. It doesn't matter, I can also draw this child this way. It will not make any difference. Even I can draw this child this way. Okay, it won't make any difference. All these properties should be maintained, that B2 should have 2 children at root. Yes, it has 2 children at root. B2 should be formed using two B1 trees. This is a B1, this is a B1. Yes, it is being formed using two B1 trees. And the root of one B1, the root of one B1. So this is my one B1 will be the leftmost child. Yes, it is the leftmost child of the other B1. Right? This is my other B1, this one. This one is my other B1, correct? So now we were looking at B3, correct? So for in case of B3, it is saying that the root of one B2, because here K minus 1 is 2, so the root of one B2 will be the leftmost child of the other B2. So this is one B2 and this is another B2. So the root of one B2, let us consider the root of this B2, it will be the leftmost child of the other B2. So this is my other B2, leftmost child of the, you can write here, root of other B2. Root of other B2. So it is the this root is the leftmost child of this root. So this actually is my complete B3. Okay. So I'll draw it again over here. So as you can see, this complete tree, what I've got is B3. And or the binomial tree with order 3, right? So over here B3 should have 3 children at root. Does it have 3 children at root? Yes, 1, 2, 3. B3 can be formed using two B2 trees. Yes, it is formed using two B2 trees. This is one B2 tree and this one is the other B2 tree, right? And the next rule is the root of one B2 will be the leftmost child of the root of other B2. So the root of one B2, this root will be the leftmost child of the other of the root of other B2. Yes, it is. So this is my B3. Now let us draw B4 together. Okay. So B4 will have four children at root. We will look at that rule for cross-checking our B4. And B4 can be formed, or the binomial tree with order 4 can be formed using two B3. So let us draw two B3 first. So here I have drawn, here I have drawn two B3, right? This is my one B3 and this is my second B3. And we know that B4 will be formed using two B3 trees, okay? And the root of one B3, let us consider this root of this B3, will be the leftmost child of the root of the other B3. So this is the root of the other B3. So this root will be the leftmost child of this B3. So as you can see, it is the leftmost child. And so what is this? This entire thing that we have drawn is actually, this entire thing is our B4, okay? According to the first rule, the root of B4 or the binomial tree with order 4 should have 4 children. So does it have 4 children? 1, 2, 3, 4. Yes, so this is our B4. Okay, so these are actually binomial trees and these are formed using these rules. Okay, as you can see, binomial trees are not necessarily balanced trees, right? They are not balanced. Moreover, they are also not binary trees, right? They are also not binary trees, because here you can see that a single node has more than 2 children, right? So here we saw B0, or a binomial tree with order 0, B1, B2, B3 and finally B4. So B5 will be formed using 2B4, B6 will be formed using 2B5. You got my point? So these are binomial trees. Now let us look at some properties of binomial trees. So these are the 4 important properties of binomial trees. We will prove and understand all these properties one by one, because I don't want you to mug up any of the properties. I want you to understand them so that after this video, even you can prove all these properties yourself. So let us talk about the first property. It says that there are 2 raised to k nodes in a binomial tree with order k, or in a binomial tree bk. So it says that if suppose there is a binomial tree with order k, so here I have drawn a B3, this complete binomial tree is a B3 because the root has 3 children, 1, 2, 3, correct, of this binomial tree. So and this in the red is a B2 and this in the blue is a B2, and the as according to the rule I have made this B3, okay. So now I have to prove that there are 2 raised to k nodes in a binomial tree Bk. So I'll prove the first property using mathematical induction, okay. So if we talk about, so using mathematical induction, if you talk about the base case, let us take B0, okay. So in case of B0, it should have 2 raised to 0 nodes or 1 node. Yes, we saw earlier that B0 is actually represented like this. So yes, this is true. So base case is true. If we talk about the inductive step, let us consider that this property holds true, that the first property holds true for a binomial tree Bk minus 1. So we can say Bk minus 1 has 2 raised to k minus 1 nodes. So this is true, right? This is the inductive step. So now when we prove for number of nodes in Bk, so actually what is Bk? So if we talk about B3 over here, what is actually B3? B3 is a combination of 2 B2s, right? So in this case, if k is 3 and k minus 1 will be 2, so B3 is actually a combination of 2 B2. So the total number of nodes will be twice of what is there in the binomial tree with the previous order, right? So in that case, what we are doing? We are actually combining 2 B2s to make B3. In the same way, we are combining 2 Bk minus 1 binomial trees in order to make a Bk binomial tree, right? So here we can write that the number of nodes in Bk will be number of nodes in one Bk minus 1 plus number of nodes in the other Bk minus 1, which we are combining both of them, right? So this will be equal to number of nodes in one Bk minus 1 plus number of nodes in other Bk. So this will be equal to number of nodes in one Bk minus 1 plus number of nodes in other Bk minus 1. So what is the number of nodes in Bk minus 1? What we assumed, it is 2 raised to k minus 1 nodes. So 2 raised to k minus 1 plus, again for another Bk minus 1 also there will be 2 raised to k minus 1 nodes. So this will be equal to 2 raised to k nodes. And isn't this written in the property that a binomial tree Bk should have 2 raised to k nodes? So we have proved it, that any binomial tree Bk should have 2 raised to k nodes using mathematical induction, right? So now let us look at the second property. So the height of the Bk tree or height of the binomial tree with order k should be k. So what is the height of a tree? So this is height 0, this is 1, this is 2, and here it is 3, right? This height is 3, this is 2, right? So this height is 0, 1, 2, 3, right? So these are height, or you can also call them depth. Okay, so now it says that the height of the binomial tree with order k should be k. So first of all, again we can solve this using mathematical induction. So what is the height of B0 tree? B0 tree is actually represented like this. So as you can see, this is the height starts from 0. So its height is 0, right? And it says that the Bk tree should have height k. So here k is equal to 0, and this thing is true for the base case, right? So base case is done, right? Because we proved it for in case of k when k is equal to 0. Now let us talk about the inductive step, okay? In the same way how we assumed in the first property, we will assume that the second property holds true for a Bk minus 1 tree, right? Or for a binomial tree with order k minus 1. So height of Bk minus 1 tree, let us assume it is k minus 1. So this is our assumption, okay? Now just try to understand that how do we form a Bk tree. So a Bk tree, or in this case let us assume a B3 tree, is formed using one B2 and the other B2, right? So suppose you know the height of B2, right? You know the height of B2, or in this case let us assume B2 as Bk minus 1. You know it is 2, So you can directly tell me that whatever will be the height of B2, the height of B3 will be 1 more than that. Why? Because what is B3? B3 is actually 2B2, but the other B2, this B2 in red, is shifted one level downwards. That is why it is starting over here from 1 rather than 0. So whatever will be the height of B2, the height of B3 will end at one level down, right? Because this B2 will take as much height as this B2, but it is starting at one level down, so it will end at one level down. So this entire B3 will end at one level down than the height of B2, right? So we can say that the height of BK tree in every case, and this will happen in each and every case, is height of BK minus 1 tree plus 1, okay? So what is the height of BK minus 1 tree? What we have assumed, it is K minus 1 plus 1. So the height should be K. Is this what is written over there? The height of the BK tree is K. Yes, we have actually proved it now, that the height of the BK tree should be K using mathematical induction. Now let us look at the third property. So the third property says that there are exactly these many nodes at depth I in a binomial tree BK, okay? You can consider here depth and height as same, okay? Both are the same things. It says that there are exactly KCI nodes. So this is actually binomial coefficient, okay? And so there are exactly binomial coefficient number of nodes at depth I in a binomial tree BK. So how do we prove this? Let us try to prove this property using by looking at this binomial tree B3. Now just pay attention over here, that if suppose we are considering this depth 2 in the binomial tree B3, okay, so what all nodes will it contain? First of all, it will contain number of nodes in a binomial tree B2 at the same depth. If you look closely over here in this blue, a B2 is also starting at the same point where this B3 is starting, right? So a B3 at depth I will contain the number of nodes for a B2 at depth I, right? Like for example this node. But it will also contain, so a B3 at depth I will also contain the number of nodes in a B2 at depth I minus 1. Why? Because there is a B2 starting at one level down than where a B3 is starting. Because as you can see over here, this is the root of this B2 and it is starting at one level downwards than where this B3 is starting. At depth I, the number of nodes in B3 will be equal to number of nodes in B3 equal to number of nodes at depth I in B2 plus number of nodes at depth I minus 1, because for this B2 it starts from here, so depth is 0, 1, 2 for this B2, whereas in case of B3 this depth has reached to 2. So this depth of 2 will contain the number of nodes of B2 for the depth of 1 plus number of nodes of B2 at the depth of 2 plus number of nodes depth I minus 1 in B2, right? So I'm making this a general formula where my k is equal to 3. So instead of 3 I'll write bk, and here I'll write bk minus 1. Again here I'll write bk minus 1, right, when my k is equal to 3. So this is the formula that we understood with the help of that example. So now if you pay attention, I can write it this way: dki, or the number of nodes for binomial tree k at depth I will be equal to number of nodes for binomial tree k minus 1 at depth I plus number of nodes for binomial tree k minus 1 at depth I minus 1, right? I have just written this formula symbolically, okay? So let us assume through mathematical induction that this property, this third property, holds for binomial tree k minus 1. Okay, let us assume that it holds for the binomial tree k minus 1. So we can write this as k minus 1 I plus k minus 1 I minus 1. right? So this will be k minus 1 ci plus k minus 1 ci minus 1, right? I've written the same thing. Now let us continue this thing over here. Now let us continue this over here. So this will be k minus 1 factorial I factorial k minus 1 minus I factorial, right? Plus this term k minus 1 factorial I minus 1 factorial k minus I factorial. Okay. So now if you solve this, if you simplify this, you have to write this I factorial as I into I minus 1 factorial, and in the same way you have to solve this. So I'm not doing this calculation. So finally if you do this simplification, the final answer will come out as k factorial I factorial into k minus I factorial. So the final result will come out as this. So what is this? This is the binomial coefficient, right? The same binomial coefficient that we need to prove. Now you will understand that why binomial trees are known as binomial trees. Because for every binomial tree of order k, the number of nodes at depth I is actually a binomial coefficient, right? So I hope you got this point, that why these trees are known as binomial trees. Now let's talk about the last property. The maximum degree of any node in a n-node binomial tree is log n. So this property says that the maximum degree of any node in a n-node binomial tree is log n. So what is the degree of a node? Degree is equal to number of children of that node, right? And so it says that the maximum degree of any node in a n-node binomial tree is log n. Now I'm not proving this property. I want you to prove this property for binomial tree, and please write it down in the comments. So now we have covered this and this, right? So we have learned what is a binomial tree, and we have also learned the properties of binomial trees and also proved them. In the next video, we will learn these three things: that what is a binomial heap, and how does a node in a binomial heap looks like. Then finally, what is the advantage of binomial heap over binary heap, and sometimes even over leftist heap. So see you in the next video, where we will learn these three topics: 1, 2, 3.